All right, hi, Year 11. This is Mr. Lim here again, and this is Friyays 4. This one was done fairly well. Thank you very much for the 15 people who actually sent in stuff by last Friday. Those ones provided a good bit of information, but if you sent anything after it, you're not getting marked. All right, so please try and send stuff in earlier. Don't forget, you've got lots of stuff to do on these holidays. Please send in stuff early to get checked. All right, so let's go through this ideas. Okay, so number one, this is the above system, all right? And this above system was cooled from T2 to T1. Now, this bit here is a bit tricky, okay? You've really got to make sure that you read the stuff here because a lot of people went, oh yeah, T1 to T2, and then made information about that. All right, so you've really got to read the information that its above system was cooled from T2 to T1. All right, so which of the following is correct interpretation of the above energy distribution diagram as the temperature decreases from T2 to T1? Okay, so T2 going to T1, all right? The activation energy. So you should recognize that the activation energy, when you change the temperature, does not change. The activation energy only changes when you add a catalyst. This is not talking about the proportion of particles with sufficient energy, all right? This is talking about the actual value of the activation energy. So the activation energy remains the same, which means that you can eliminate B and C because it's not going to be the activation energy decreasing. All right, so then you look at the proportion of successful collisions between particles. So if you cool it down, the proportion of successful collisions between particles is going to decrease, not increase. Okay, that's why this is a bit tricky because you're going from T1 to T2. Okay, so therefore, it's going to not be A, right? But you can also have a look at the last bit, the yield of COCl2, right? So when you cool it down, it's going to favor the exothermic reaction. They're both going to go down, but the endo is going to go down more, which means the exo is going to be favored. And so the exo happens to be the forward reaction, which means that there's going to be more of the COCl2. All right, so that means it's increasing here, which is what doesn't make a difference for the process of elimination. All right, so that one was D. Please make sure that you read the question really carefully because that was where I think a lot of people went wrong. Okay, next. Okay, so this question here. Okay, so this question here was a bit tricky because the system attained equilibrium with initial volume of 5 liters. The volume of the container was increased to a new volume of 20 liters. So I always like to, in my head, say, okay, or with my hands, draw out or mimic out what is occurring. It's going from 5 liters to 20 liters, which means it's getting much larger. All right, because it's getting much larger, and then I always go through the 5 steps. The forward rate of reaction is going to go down. The reverse rate of reaction is going to go down. Okay, so both of those rates of reaction are going to go down. All right, so we can immediately eliminate, right, the first two. Okay, so neither of the reverse rates of reactions are going to go faster. They're both going to go slower. All right, and so now we only have to look at the partial pressure of the CO gas. Now, if you expand it, right, I know that the partial pressures of all of those, which is effectively the concentration of all of those, are going to go down. Why? Because I've increased the volume. So everything goes down, right? And if everything goes down, the partial pressure is going to be lower at its new equilibrium point because it's not going to go back up above its original amount, right? Especially because you kind of quadrupled the amount you're going to, quarter the concentrations, right? So everything's going to go down and then they're going to find a new equilibrium. Again, it's not going to go 4 times as much, right? So that's that one there. You're going to be able to remove by process of elimination the idea is that, okay, it's not going to go faster because the volume increased, and then it's not going to go higher because every partial pressure went down. All right, so there's that one there. The next one, 3, the following changes were imposed on the system in various experiments, blah, blah, blah. Okay, so let's have a look. How many of these changes will result in a higher partial pressure of COCl2 once equilibrium is established? Okay, so again, this is partial pressure, so let's have a look. Addition of a catalyst. Well, that's going to increase both rates of reaction, but not going to change the overall net position, right? So that one's not going to make a difference. Addition of neon gas, addition of an inert gas, not going to make a difference. Okay, decreasing the volume of the system. So I would always, do this with my hands and say, okay, it got smaller. That means that the partial pressure of everything's going to go up. Okay, and you're going to squeeze everything together. That's going to make it an increase in partial pressure overall. Okay, because it's not going to go down, even if it is favored. All right. So, but we should actually work out what happens. So let's go through that. The forward rate of reaction is going to go up. The reverse rate of reaction is going to go up. Which one's going to go up more? The process that is going to make less particles is going to be affected more. Which one makes less particles? It's the forward rate of reaction. So the forward rate of reaction is going to go up more. So there's going to be a net forward. And if there's going to be a net forward, there's going to be more of the products, which is actually what you are expecting for COCl2, right? You want a higher partial pressure, so therefore it's going to go up. All right, and then the addition of more chlorine gas, that's going to have a net forward rate of reaction. Okay, that's also going to have a net forward rate of reaction because the forward rate of reaction is going to go up. The reverse rate of reaction is going to stay the same, and therefore it's a net forward rate of reaction. So it's this one and that one, which makes that 2. Okay, let's have a look at this one here. Okay, so there's a bit of information here that you need to take into account, right? So you should recognize that the volume has no effect on the pH, okay? Because if you add in more of this stuff, it's not going to make it that much of a difference. Volume makes a difference in terms of the number of moles that are present, but it doesn't make a difference in terms of pH. So volume there, bit of not important information. The concentration is important, and you'll notice that this one here is 0.5 and the other here are 0.1s, right? So the question is, this one here, the hydrocyanic acid is 5 times more concentrated. So in theory, you would have to think it's going to be more acidic, but then you also have to take into account the Ka values. And this is something that we've been poor on previously, but you've got to remember that the Ka value is a representation of how much products there are compared to how much reactants there are in a equilibrium system. And the Ka is for the hydrolysis of these acids. So effectively, how much products there is effectively how much it ionizes. And so therefore, the stronger the acid, the higher the Ka. Or alternatively, the weaker the acid, the lower the Ka. So which one has the highest? This one here is the highest, and this one here is the lowest. Okay, so we can eliminate out then the dihydrogen borate ion, right? We can eliminate out the benzoic acid because that one is at the same concentration, but they are lower than the nitrous acid. So then the next question is, which one is going to make more of an effect? Is it going to be the fact that this one here is 5 times as concentrated, or this Ka is greater? Then you look and compare this Ka versus this Ka, and this Ka is times 10 to the negative 4, and this Ka is times 10 to the negative 10, which actually means that this is like 1,000,000 times stronger than this one here. Okay, because just because it's a small difference here doesn't make a difference. It's this times 10 to the negative 4 times 10 to the negative 10, right? This is 1,000,000 times stronger, right? So because this is 1,000,000 times stronger, it doesn't matter that this is 5 times more concentrated. Okay, so therefore that's going to be nitrous acid. Okay, but you have to remember this part here we've been bad on. So the Ka is a ratio of products to reactants. The higher the value, the more products there are, and therefore the more ionization for acids, or bases for that matter, and so therefore the stronger the acid. All right, let's move on. This one here, this is just about memorization. Please, please, please memorize this at some point. All right, this one here is about understanding the scale of pH, okay? You should recognize that pH is a logarithmic scale. So to go from pH 1 to pH 2 to pH 3, there is a 10 times strength change, right? So effectively pH 1 is 10 times stronger than pH 2, and pH 2 is 10 times stronger than pH 3, which means that there is an overall 100 times change here, right? And therefore, to make this solution to be a pH of 3, you would need to have a 100 times dilution, and a 100 times dilution of 25 goes all the way to 2,500 mils. Okay, so this is 2,500 mils, but remember how much water should be added. You need to get to 2,500 mils, which means that you need to add in 2,475 because you have to also include the 25 mils initially. All right, you can also work this out by calculation. All right, so by calculation, what you would do is you say, okay, then I've got a pH1 solution, which is effectively 0.1 mole per liter, and a pH3 solution, which is effectively 0.001 mole per liter. So I can work out the number of moles of H plus ions I have in the 25 ml sample. So the number of moles would be 0.1 times 0.025, okay, which is some value, 0.0025 moles. All right, and then I have to work out what volume do I need to have to get this to the new pH that I want, or the new concentration that I want is 0.001. All right, so I would do V is equal to N on C. You need to really make sure that you are remembering the ways to rearrange that equation. All right, and this is the new concentration I want, and so that would be some value, 0.0025 by 0.001, 2.5. So this is 2.5 liters, so this is the value that I need to get, and therefore the volume of water added would be equal to 2.5 liters, subtract the initial 225 mils, which is equal to 2.475 liters, which is that value there. All right, so let's have a look at the next one. Okay, so tells you that you've got NH3 in here and HCl there, which means that the pH is going to go from high to low. Okay, happy with that idea, that it's going to go from high to low. So therefore, if it's going to go from high to low, and we know that it's also going to make the salt NH4Cl, this is a salt that's going to be produced, or a product's going to be produced, which means that it's going to have an acidic EQ point. Okay, so because it has an acidic EQ point, we should pick methyl orange. Okay, and because it's going from high pH to low pH, we're going to be going from yellow to red. Okay, which effectively means that you're going to go from yellow to red, which means that at the equivalence point, it's kind of be in that orangey area in between. So that's how you pick that one out, right? You look at the information that's given to you here, work out where the pH is going to go high to low, work out what the products are, and then you pick out the right indicator. Okay, let's move on. Okay, so this is the question here, right? So this one here, most people did well. I think we've practiced a lot of titration as well, right? The one thing that I would like to highlight is that when you're given such a great, beautiful graph like this, you've really got to use the grid lines, okay? So you can see the grid lines, it is exactly on this particular grid line. And if you track that grid line all the way to the bottom, it reads to 24 mils here. And if you can't read this scale, like, you got to work on that. So 24 mils between there and there. So this is the calculation then. As I said, you always draw a diagram. You've got 24 mils inside your burette, or being delivered by your burette of 1 mole per liter. Then you've got of NaOH, then you put it into the diluted CH3COOH, which comes from the 500 mil, which comes from the 100 mil here. All right, always draw that out. I would always highly recommend writing out what you've got there as well. Okay, now the things that were done poorly here were the fact that people are still not putting in their, their equations. Please put your equations in. Please make sure that you know how to rearrange this concentration equation. All right, the concentration is equal to N on V, right? Not N times V. That was a common mistake, right? And then this one here, please know when it's an aliquot and when it's a dilution, okay? I always like to write this one out, even though I don't need to write this one out, recognizing that when this is diluted, right? When this is diluted, you do not, the number of moles stays the same. But when you take out a portion of it, it becomes an aliquot. So you use the aliquot equation here to change the number of moles, because the number of moles will be different, right? But in a dilution, the number of moles will be the same, the concentration will change. Okay, so We might have to practice that a bit. I might be putting those into some new quizzes soon, right? But that's that question there, right? This back titration here was done reasonably straightforward, but there are a couple of things that a lot of people missed, okay? So this was the thing, right? A couple of common areas that people missed. All right, so a couple of areas that were people were making mistakes, still not putting this equation in, okay? Making sure that you get this equation, because this equation is important because it actually has an effect on the stoichiometric ratio, all right? You should recognize that the equation up here, right, there is a 2-to-1 ratio between the sodium hydroxide and the acetylsalicylic acid, right? So there's a 2-to-1 ratio, so that does make a difference, right? Other areas, again, right, some people were still making this mistake here. When they did this one here, they went straight to the acetylsalicylic acid. So you can't just assume that this number of moles used is this, okay? Because these two aren't necessarily equal. There's going to be some stoichiometry between it, okay? The aliquot equation here was done meh by some people, but one of the most common things that was done wrong is that you needed to recognize that this is 5 tablets of the vitamin C, the acetylsalicylic acid, and it asked for 1 or aspirin tablet, okay? So the 5 tablets to 1 tablet changes it just at the very end, right? You've got to read that to make sure that you recognize that division by 5 there. And then lastly, this bit here, right? So this bit here was the asking what changes can be made here. And so what I would always suggest, remember, is that if you're still struggling with the titrations, if you're struggling with memorizing other stuff, go work on those things first, all right? Because those things are going to be more common and easier for you to fix then to try and work out these, all right? But when you do get to these ones here, you give it your best shot and work out, really read what they're asking you and work out what the changes are going to be. So let's have a look. The first one here. Oops. So I would always remember to have this diagram next to it so that you can have a look and see where things are going. Predict and explain how the calculated mass of acetylsalicylic acid would be different in the cases of the following changes to method. All right. Now, if it's predicting how it would be different, it can also not be different. Okay. So this one here, a couple of options here. If this is hydrochloric acid instead of sulfuric acid, so this here is hydrochloric acid, the equivalence point here is going to change because you're now going to have sodium chloride instead of sodium sulfate, which means that the EQ point is no longer going to be basic, which means it's going to be neutral. If it's going to be neutral and you've used a phenolphthalein indicator, now a couple of things. Where there's a strong acid and a strong base, the phenolphthalein is actually still an acceptable indicator to use. And it's acceptable because the change in pH is very large between a strong acid and a strong base, okay? So, because the phenolphthalein is still an acceptable indicator to use, this actually means that the mass that you calculate is going to be the same unless you've screwed up the hydrochloric acid and sulfuric acid, unless you think that you're using hydrochloric acid instead of sulfuric acid. All right, so this question really isn't worded very well. It might have been better to say that the person used hydrochloric acid but thought they were using sulfuric acid. But if you're just using hydrochloric acid and you know you're using hydrochloric acid, it's actually not going to make any difference to the calculation. All right, so there's going to be no change, right? Other than the fact that the volume is going to be a bit different. Okay, so that's for the first one. In theory, there's no change. You've got to remember that phenolphthalein is an acceptable indicator to use when I've got a strong acid and a strong base, because the change in pH is going to be so large. It's going to go from 10 or 11 all the way down to 3 or 4. So it's not going to make a difference that you use phenolphthalein instead of methyl red. Okay. Next, methyl orange in the titration as opposed to phenolphthalein. So go back to an EQ basic point, all right? Or EQ point being basic. So you've got methyl orange. When you change the indicator, you've got to think, okay, how is the pH going to change? It's going to go from high to low because you've got the NaOH in the conical flask and the acid in the thing, right? So you're going from high to low. That means it's going to go, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. So that means that if it's using methyl orange, right, your titer is going to be too high. If your titer is too high, tighter here is too high, you're going to think that there's lots more excess here. A lot more excess here. If you're going to think that there's a lot more excess here, there's more excess here. If there's more excess here, that means you think that there's less used. Less used. If you think that there's less used, right? If you think that there's less used, you think that there's less inside here, which means that the mass there is going to be lower. Okay, this is a bit tricky because it's a back titration, and this would be different if it was just a normal titration, but you've got to try and track along with all the ideas. Okay, filling above the line when diluting the reaction mixture in a volumetric flask. Okay, so your dilute, this one here is to dilute. That means the tighter volume here will be too low, and if the tighter volume here is too low, it's exactly the it's the opposite of what we said last time. If the tighter here is too low, you think that there's not a lot of excess. If there's not a lot of excess, you think that there's a lot used. If you think there's a lot used, you think that the mass of these is going to be greater than it actually is. Okay, and higher grade pipettes, that's not going to make a difference. To the mass calculated, it's just going to make it more precise, but the accuracy is not going to change. So the mass is going to be the same, but you're just going to have more precise information. All right, and this video has already gone too long, so adios.